There's a lot of unnecessary mystery about proofs, and there's some necessary mystery as well, but the emphasis always seems to get mismatched. What's the proper mystery and what shouldn't be mysterious? So, proofs is not a thing. What we do in mathematics and in computer science and in other areas is we prove theorems. Theorems are the things that we're looking for, and we don't know that the theorem is correct until we have a proof for it. But what we really are interested in is theorems. And so what I'd like to do is talk about some ways that we get theorems and a little bit about how we prove them, but a little bit more about why we prove them, and we'll go on from there. So there's a three-step process that goes into this whole theorem proof picture. And sometimes we have a theorem, and it's just a calculation. It's a computation. So sometimes if it's a really hard computation, people will call it a theorem. And so when you study calculus or advanced calculus, you've got Stokes's theorem and Green's theorem and so forth and so on. And those are general calculations, general methods for doing some kind of calculation and making it easier. So that's the way you find a theorem. Take some difficult family of calculations and find a way to make them easier. So that's a thing that you can do. More broadly than that, one thing that you can do is develop an algorithm for solving a certain kind of problem. And we're going to see some of those later in this semester when we start to look at some of the graph algorithms. And so that's a way to find a theorem too, is to prove this algorithm solves this problem. Sometimes you just notice a pattern and you want to say, hey, I wonder if that pattern always applies. And so you prove that it always applies, or maybe you prove that it doesn't always apply. And so the whole motivation here that gets left out of a lot of discussions about proofs is we're not interested in proofs. We're interested in theorems, and theorems are a thing that we do because we're interested in them, and proofs are a thing that we do as an auxiliary toward having the theorems. And so we're really interested in theorems. And so for right now, I'm going to talk about some theorems and how we might have found them, or how we might have just come to ask the question, and we'll go on from there. So, proofs. Number one, find a theorem to prove, and that comes from doing the work that you do in computing or math or physics or any other area where there might be theorems. That's the main goal. The secondary goal is to find a proof, and this is, there is no general method. It depends on what realm of knowledge that you're talking about, so it depends on the topic. If I'm doing a, say, calculus proof, then I'm going to be using calculus techniques. If I'm doing a graph theory proof, I'm going to use graph theory techniques. If I'm doing a set theory proof, which is what we're going to do next, we'd use set theory techniques. Or you could use logical techniques like mathematical induction. But the technique that you use, many of the greatest advances have come from borrowing a technique from a faraway topic and thinking of a way to apply it to something that you're interested in. And so there's no general method. There's nothing that you can do other than keep studying results in computing and in math and in physics and in engineering. And you keep studying results and you see how people establish that theorems are true and go from there. There's a third step that's also neglected. So number one was you got to find theorems. Number two, that's the real goal. Number two is you have to prove the theorems. That's part of what makes them theorems. And number three is you have to convince people that you have a proof. So that's writing the proof. And that is a little bit more mechanical once you actually have the proof, but it's something that has been a source of difficulty for like everybody forever, because it's a very different process from finding the proof. And finding the proof is a very different process from finding the theorem. And finding the theorem is what we're really interested in. So I want to talk about a couple of theorems, and maybe not even go into what the proofs are, but just talk about what the theorems are and where they might have come from. And so they're on the back of this paper. So here's a way that you might find a possible theorem. Let me just make a quick note here. So one is we want theorems. And we'll talk a little bit more about what that is. Number two is that means we need proofs. And number three is we need to explain the proofs. When you prove something, then you have to explain it. So that's our real goal. Find theorems, find proofs for those theorems, explain to people why those proofs work. So, okay. And there's a lot of creativity involved in all three of those steps. So let me do something that is a way that people might find a theorem. So this is an example theorem, and it's something that is very elementary as far as how much mathematics you need to have studied to do it. But here's an example theorem and an example of finding the theorem. So what I'm going to do is I'm going to pretend I'm a curious 12-year-old, and I'm looking at all of the squares. Squares of whole numbers. 1, 4, 9, 16, 25, 36, 49, and so forth and so on. So we're looking at squares. And one of the standard things that you can do when you're looking at a list of things is to look at the differences. So that's a thing that people do that provides a lot of insight. And so I'm going to take these are the squares, and I'm going to look at the differences. So 4 minus 1 is 3, 9 minus 4 is 5, 16 minus 9 is 7, 25 minus 16 is 9. And you're starting to see a pattern emerge, is that as you look at the difference of two squares, you're seeing the consecutive odd numbers. That's an interesting pattern. And so let me just do a couple of more. And so 36 minus 25 is 11. 49 minus 36 is 13. So it looks like we have this pattern, difference of squares and being an odd number. Now that's fine. We've only gone up to 49. If we go up to Skewes' number, Skewes, which is the largest number that is commonly used in honest mathematics. It's not used to make up a big number. It's a big number that occurs when you're trying to do a certain problem. So if you look at Skewes' number squared, I forget how many digits it has. Actually, I think I have it right here. Skewes' number, 10 to the 317th power. So the square of that has 600 something digits. Yee-haw! Okay, so do you believe that this pattern is going to continue until you hit the square of 10 to the 317th power? I don't. I don't believe anything that would go out that far. And so what we do now is we have a statement of a theorem, and then we can prove it. And the statement of the theorem is the difference of two consecutive squares is an odd number. That's not as precise as we can be, but it's a good first pass. You don't think you get it right the first time every time, do you? So that's our theorem. and it's probably expressed better in algebra. So I'm going to say i.e. for every natural number n, the difference of consecutive squares, so I'm going to write that as a difference of consecutive squares, and I'm going to write a formula for what happens here. So for every natural number n, guess what? You're going to have to prove this by induction if you're going to prove that. If you want to prove a statement that involves every natural number n, you prove it by induction. So that's a technique that we've already worked on. Anyway, so now I've got this formula. So n, I'm squaring that, and I'm taking the difference with the square of the next natural number, n plus 1. So n plus 1 squared minus n squared. And in fact, it works out to be 2n plus 1. Now, this is about theorems, not about proofs. So I am not going to go through the proof of this theorem right now. But the idea is that you could see that there's a way to discover a theorem by playing with some data or looking for a pattern. It might be a geometric pattern. It might be some other kind of pattern with graphs or trees or something. You're playing with something, you see a pattern, and you find a way to establish that that pattern holds in all the cases that you're interested in. So that's a way to find a theorem. And so look around for patterns. And there we go. So that's a very good example of a theorem and how to find it. So you find it by doing something else. I mean, professional mathematicians, what they do is they look for theorems, but they look for theorems in a certain topic area. So my primary topic area is algebraic geometry, and without going into any detail about what algebraic geometry is, I read books and papers about algebraic geometry. I talk with people about algebraic geometry. And after a while, every little bit, like a year or so, I go, oh, hey, there's an interesting pattern. And then I go and try to prove it. So you come up with theorems by doing interesting stuff. Okay. So let me show you another example theorem. And I'm going to assume that this is something that you would have seen in a previous computer science course, because this is usually the second example that people do of a recursive algorithm. So let me run, and I'm not going to go into proving why the algorithm works. So this is the GCD, greatest common divisor. And there are two separate problems here. One is developing this algorithm, but there's another kind of thing I would like to look at. So to find the GCD of two numbers, what you do is, I'm going to use computer notation. This is, let's say, they've got this relationship. So this is the algorithm. And so where did it go? There it is. There it is. So if I want to find the GCD of two numbers, what I do is take the remainder and take the smaller number and move that up to being the bigger number, and then take the remainder. So for example, the GCD of 48 and 20, well, to do that, 48 is 2 times 20 plus 8. So the remainder is 8. And so this is equal to the GCD of 20 and 8. So that's the step that you do. And so, pardon me a second. I don't want to do updates. Sorry, this is, one of those things that even Apple has been Microsofted. So, okay, so we have this GCD algorithm. So that is all just fine and dandy. And you usually do this with very small numbers. But let me ask you about the following situation. I'm going to write down a couple of big numbers, 3, 2, 4, 6, 3, 9. And 2, 1, 7, 1, 1. And I'm going to say, what if we needed the GCD of these two numbers. This is something that could actually come up in a cryptography problem where GCDs come up a lot. So I have these two rather large numbers, at least large in human terms, and I'd like to find their GCD. And so I'm going to start in on this long process of doing division of the bigger one by the smaller one and getting the remainder. And good luck doing that division correctly by hand. That's a hard one. It's just there's too much stuff there. Too many opportunities to make a little subtraction error. Anyway, you're going to do the division. That's not part of the theorem. You're going to do the division. You're going to take the remainder, and so what you're going to do is you're going to replace this by the GCD of 21711, and we don't know yet. So that's what the algorithm says to do. So let me ask you this very important question from a computational standpoint. Is this going to stop? Is this algorithm, does it terminate? And in fact, that is a theorem. So the theorem that we're discovering by looking at this and by pushing our comfort level a little bit by using larger numbers, the theorem is that this algorithm stops after a finite number of steps. That is a theorem. It's a theorem in computing more than it is a theorem in math, but and so there's the situation. So we have discovered a potential theorem, and so that's the first step of the outline of what it is that we're trying to do. You want to find theorems, and then you have to worry about how to prove it. And how to prove it is going to depend on noticing a lot of detail, or maybe bringing in details from something else, or heaven knows. Even heaven doesn't know. Nobody knows. I mean, there are potential theorems that have been out there for literally for centuries that nobody knows how to prove yet. And so there's a situation. So there's an example, or a couple of examples of theorems. One I didn't write down, but would be some long, complicated calculation. Calculus is not a prerequisite for this course, so I don't want to mention specific calculus theorems, but let me just say that there are theorems in calculus that are really useful, and we do them, and so we discover this pattern, and then we prove that pattern holds, and then we go on to do interesting stuff. That's the whole point, to go on to do interesting stuff. We have this example theorem about the difference of squares, and that was just by playing around with some numbers because we were bored, and we saw a potential pattern and formulated a theorem that encapsulated that pattern, and that theorem does happen to be true. It takes a little bit of algebra and mathematical induction, of course, because it's a theorem about the natural numbers. And then we have kind of more of a theorem in computing. So the mathematician will worry about with this greatest common divisor. Oh, are those two greatest common divisors really the same? I do this thing, I do this thing, I change it from this and this to this and this. Does that have the same greatest common divisor? That's a different theorem, but which in fact is true, but you have to prove that using kind of number theory techniques. But the computing theorem with any algorithm is, hey, does that halt? Is that going to stop, or are we just going to go into an infinite loop? And so that's a theorem, that this algorithm does not go into an infinite loop, and so then we would have to sit back and try to find a proof of that theorem. So we're not interested in proofs. Oh, I'll probably lose my American Mathematical Society membership card if anyone hears me say that. We're not interested in proofs. I'm going to say it again. I'm going to risk everything. We're interested in theorems. Theorems enable us to take patterns or questions or calculations or algorithms and make them general and make it so that we can apply them to do interesting stuff. So we're interested in interesting stuff. Theorems is how we can do more interesting stuff, and proofs, that enables us to use the theorems with confidence. Okay, so I didn't prove anything, but it's important to know what it is that we're aiming at, and what we're really aiming at is theorems. And then so next will be to look at some theorems from set theory and talk about how to prove them. But for the moment, remember, what we're interested in is theorems, and there is no general way to prove them. You just have to understand what it is that the topic that the theorem is about, and probably some other topics as well.